So in this video we're going to talk about the cheapest link algorithm, which is another approximate algorithm for solving TSPs. So the steps to this algorithm are you just continually pick the edge that has the least weight, and then you redraw the graph using those edges, and then you see what the TOR will be. Okay, there's two things you can't violate, and it's basically why you have to redraw the graph. Redrawing the graph is not an option. It's something that you really have to do. So, and the reason is because, by redraw I mean you can either draw what you're doing over here, or if you already have the graph drawn, you can just highlight the edges that you're choosing. But if you have a chart, which I'm probably going to do another video where we use this algorithm based off of a chart. While you're using the chart, you have to continually draw a picture that goes along with it. It's not an option, you have to do it. And so you don't violate two things. You can never have three edges coming into the same vertex, because that would mean that you went to that vertex, left it, then came back, which you're not allowed to do because we're only allowed to visit each vertex once. We're trying to make a Hamilton circuit. And you can't close off a circuit before you finish the whole circuit. In other words, you can't go from B to D to E to B. Okay? And that's the same reason as the last one actually. It's rephrased differently. Because if you went from B to D to E to B, we're still not done. So then you'd have to go from B to A or B to C. So then you would have three edges coming into the same vertex, which you're not allowed to do. Okay. So, like I said, we're just picking at each step the shortest edge, or the edge with the least weight that's available. And we're trying not to violate any of our two conditions that we're not allowed to violate. And then we're going to try to make a Hamilton circuit. So, obviously, if you don't understand what I just said, read about it. Stop the video right now, read about it. Cheapest link algorithm, it's in the book. Come back, you have a little idea about it. Start watching the video again from the beginning. Obviously, I'm going to give an example, and the example's right here. Sometimes the best way to understand a problem, instead of me just saying what the steps are, is to watch the example. So now we're going to do this example. Okay. So if you look at this graph, the edge that has the least weight is the edge that goes from D to E. It's 25. So I'm going to draw that. Okay. The edge that has the least weight that's remaining is the one that goes from E to C. It has a weight of 26. Okay. Oh good, I made this. The way I made this actually is going to show something. The next lowest weight remaining is 33, but we cannot use that because you cannot complete a circuit at any time while you're doing this until you actually have a Hamilton circuit where you visited every vertex once and now you just have to go back to the beginning. You cannot use this because if we use this edge, we wouldn't be done yet, and then we'd still have to go someplace else. Which means not only have we completed a circuit, but we would have three edges going into the same vertex, which you can't ever do. Okay, because that would mean that you've been there, left, and came back. But we're only supposed to visit each vertex once. So we cannot choose this edge, even though it's the one with the least weight. Okay, so let's look at the one that has the next lowest weight. And it looks like it's this one, 36, but we can't use that one either because then we'd have three edges going into E. We wouldn't have completed a circuit, but we'd have 3 edges coming into E, which you can't do. So we can't use 36. What's the next one? 38. 38's okay. We haven't completed a circuit. We haven't, we don't have 3 edges coming into one spot. Notice that each edge that you pick doesn't have to be connected to something else. This isn't connected to anything we have down here, but that's all right. Okay. We haven't violated any of our conditions. What is the one with the next? The next smallest weight is 40. We can do this too. We haven't completed a circuit. We don't have 3 things coming in, 3 edges coming into one vertex, so that's good. Sorry that I stepped out of the frame. Some of you might like that, but I'd rather stay in the frame for some reason. Well, let's look at our let's look at what we have drawn so far. We've been every place. We've been to A, B, C, E, D. That's every place. So we just need to close the circuit now. How do you close the circuit? Well, you look at the 2 edges, the 2 vertexes that only have 1 edge going into them. See, B has 2 going into it, C has 2, E has 2, E has 2 edges going into it. D and A are the only ones that don't. So if we connect D and A, we've completed our Hamilton circuit. What was the length from D to A? 72. Unfortunately, that's the one that has that's the edge that has the biggest weight, but you have to use it because that's how we complete our circuit. Remember, these algorithms don't necessarily give you the best tour. They just give you one really quickly that's probably not going to be the worst. So let's see what the weight of this tour was. Oh, and if we say that we're in Cortland, or C, vertex C, you would start it off by saying, okay, we're at C. Then you could either go to E or B, right? Let's go to B, then A, then D. So we went from C to B to A to D to E, then back to C. This is going to be 40 plus 38 plus 72 plus 25 plus 26. You're still going to have, since it's K5, you'll have 5 numbers to add up. You can barely, I almost went off the screen. So we have 78, 150, 201. I'm very curious to see, obviously that's probably not the best tour, but I want to see maybe if we did the nearest neighbor algorithm starting at A maybe. I just want to see what that would give us. So you get some review here. I'm going to talk about the nearest neighbor algorithm. So using nearest neighbor starting at A. So this was the cheapest link. Cheapest link algorithm gives you a tour of 201 with a weight of 201. So we're starting at A. Okay, so we're going to go from A to E. From E to D. D to C. Oh wait, yep. Then we haven't been to B yet. So you have to go to B. Then you have to go back to it. Right? Let's see what that looks like as far as the weight. 36. Notice that we didn't have to travel along the one with 72. So this is going to give us 61, 94, 94 plus 78. 172? Okay. There. So the cheapest link algorithm in this case was actually pretty bad, but it didn't take us long to figure it out either. We don't want to have to use the brute force algorithm. Obviously for K5, using the brute force algorithm wouldn't really be that difficult, but as we get higher and higher, K8, 9, 10, we don't want to have to use it. So, but remember what I said, let's pretend that we really are headquartered in Cortland. So even though we use the nearest neighbor starting at A, let's rewrite this so it starts at C. So it'd just be C to B to E to D, C to B, to A, sorry. I wish I could edit these. C to B to A to E to D to C. It's pretty similar to this, except for in the nearest neighbor one we go from A to E. Here we go from A to D. So the nearest neighbor algorithm starting at A winds up being a much better approximate algorithm in this example. So in my next video, I'm going to do another cheapest link one, but it's going to be using a chart. It'll be the same chart as the problem I did in a couple videos back.